there's one really interesting scalar product, and it's called a triple scalar product. So if you've landed here, you probably are interested in what it is or how it applies to vectors. So it does deal with vectors, and when you are studying vectors, when you have two vectors, you can of course do the dot product and you can do the cross product. But you can combine those two results and you can get a triple scalar product. Now, by just kind of definition, depending on the three vectors that you have, how you actually perform this does matter. So the cross product is always done before the dot product, and it wouldn't even make sense to do the dot product first between two vectors. So if you notice, if you're going to do the dot product, you're going to just get a scalar value, and then a scalar value crossed with a vector just doesn't make any sense. So we don't really technically have to put brackets around the cross product. We just know that it's always done first. And now the way that you're going to be aligning, so in the three vectors that you have, how do you actually compute this? Well, so long as you know how to do the cross product, so that's something which is worthwhile. I can put up a link up above there if you've forgotten. And so long as you are okay with the dot product. So once you know those two, you can certainly perform this, and it will be a scalar value that you're going to obtain. So that scalar value is going to be just a basically singular value. Now, what is it good for? Well, it does have a few applications. One of the applications, which is kind of neat, is to be able to very quickly in 3 dimensions, to be able to tell, or higher dimensions, to be able to tell if you have 3 vectors that are coplanar. So what does that actually mean, okay, to be coplanar? Well, coplanar actually would mean is if you would be drawing a plane, and that could be any plane, okay, that you have. So let's say, here is my plane. This would have been a plane in kind of 3 dimensions, okay, within here. And you would want to be able to see if you have your vectors that are actually, okay, all falling on the same plane. Now, you might say, well, I can kind of look at it and see, and they're kind of in a plane. So that's true, okay? But in 3 dimensions, it's not always that easy to be able to tell that. So, how can you do that? You can actually use this scalar product, okay? So this triple scalar product in between. Now, how it works is whenever you're going to take... Now, by the way, you can use any 2 vectors and take the cross product in between them, and then do the dot product, and then see, okay, what actually happens. And to be able to see if the vectors are actually coplanar, so they're in one plane that you have, once you take the cross product, don't forget what the cross product does. So the cross product between 2 vectors, so let's say that, we would choose this vector, and then we would choose this vector, and then we would take the cross product. So what would have happened is we would have found a vector which would have been actually perpendicular to both of those vectors. So it's either, coming out, okay, of this, so it would be creating our plane, or it's going back. Now, it doesn't really matter. And now notice, if it's perpendicular to those vectors, and again, it doesn't matter which 2 vectors you choose, then if you take the dot product in between, so if you would have now taken the dot product in between this result and the other vector remaining, and you find that this result is actually equal to 0, so if it equals to 0, that means that the 2 vectors, so the we sometimes call the normal vector, okay, from the plane, so that vector coming out or going in that you would have is going to make a 90 degree with the other third one. And that simply would just confirm that indeed these vectors are coplanar, they're in one plane. If the dot product is not equal to 0, then that third vector, okay, actually lies outside of a plane, so lies somewhere else, and therefore the vectors are not coplanar. So that is actually something useful to be able to do. Now, another application which is pretty neat is to be able to find the volume of a parallelepiped. Now, this is, very kind of, this application is because we don't always find, parallelopiped. So by the way, a parallelopiped is, so I've kind of drew it out there. So what it means is that every face that you have is a parallelogram. So no matter which face you look at, it's going to be a parallelogram, okay, on its own. And a parallelopipe just means that it's the three-dimensional geometric figure. Now, if you take this parallelopiped, so what happens is you can certainly, define this parallelopiped by three vectors, right? So if you're starting off, so this could be your first vector right here that you have in here. So that's your first vector. You can have another vector, okay, which would have been this one, and you can make, a third vector. So let's say I'm going to put this one in on the interior there. So those three vectors would define for you the parallelepiped. Now, if you want to find its volume, what it turns out to be is, so these three vectors, so if you take this, I'm going to duplicate it. So let's assume that those are the vectors. If you perform the actual triple scalar product, and because it's a volume, so we would take the absolute value of it, this would actually give us the actual volume, okay, of this. Now, you can do the convincing on your own, but it probably shouldn't surprise you at all because of the fact that the volume, right, of a parallelopipe, you can even think of a prism, right? So if you're thinking of a prism, right, the volume is base times height. Well, a parallelopipe is also kind of the base area times your height. So in order to find the actual height, you would have to find the angle in between there. So that's hence this kind of dot product that you might play in there. And then you also want to be able to find the cross product. So kind of finding the area, okay, that is defined by that. So I'm not going to try to prove or convince you that. You can certainly do it. But that's what the scalar product can be used for. So now let's calculate the scalar product just to see, all right? And then we are going to be able to find out, okay? And you can see that it's not really that difficult to do. Now, the question sometimes is from students, how do you know which vector's 1, which vector's 2, which vector's 3? It doesn't matter, right? So that's another item that you can convince yourself. So it does not matter how you choose these. So this could be V1, this could be V2, this could be V3. The actual scalar product is going to be the same, okay, that you are actually going to be doing this. And we can do, we can swap these just to convince yourself for finding out what that triple scalar product would be. So now let's assume, so if I took V2 and V3, so now I'm going to do the actual cross product, so I have to do it first. So it doesn't matter which ones you choose. So I can, let's say I'll choose these two. So I'm going to take the cross product in between these two. So let me calculate that cross product. So there's my cross product, okay, so within here. So notice it will be a vector. And now I want to be able to dot it, right? So I want to take the dot product with the third vector. Now, again, the dot product, the property, so it doesn't matter if the property, so if the vector goes in front or if the vector goes in back. So, don't forget that if you have two vectors, right? So let's say I have vector M1 dotted with a vector M2. So that's the same thing as saying, vector M2 dotted with M1. So that is exactly the same. That just comes from the properties of the dot product. So I can take this one, so the third one, -1. 3 and 1. Now I'm going to find the dot product in between here. So if I do that, this one will be a little bit faster. So that's 4, so plus -12, and then plus 3. So there you have it. So that's going to be 4, so minus the 12, so that's -8, so this is -5. So that would have been giving me the actual triple scalar product. So since it's not 0, that means that these vectors are not coplanar. So they do actually span 3 dimensions. So that's what I would know. Now, if you wanted to find out, okay, what the volume would have been made up of these 3 vectors, then you would have just taken this. Now, of course, because it's volume, so we would have to take the absolute value. So this would have been 5 of whatever units that this parallelopiped, okay, would have been set up as. So that's pretty interesting. So this is something which is definitely used, and you do sometimes use it when you have, for instance, when you're going to be intersecting planes. You want to be able to see, are the normals, for example, coplanar or something, because that's going to give you a hint with regards to, what happens and how those planes are intersecting. But that's, something for another video that you can look at. Now, just to convince you, so within here, so let's say take this example, I'm going to do it in fast forward fashion. Right, I'll just swap these. Notice I took V1, V2, and then I dotted it with V3. Let's take, for example, V1 and V3. So I'll do that. So let's say V1 crossed with V3, and then I'm going to dot it, okay, with V2. So there you have it. All right, so it's 5. So notice now, of course, if we take the absolute value, okay, of that, which is still 5, and this is exactly what we got over here. So the only difference with that triple scalar product might be if you rearrange these vectors, you might get, so they're not going to be exactly equal to each other, okay, per se. The absolute values are going to be equal to each other. So you might get a positive or a negative swap, because it just depends on how you are taking your normal, right? So as you take the cross product, notice that there's always going to be 2 different ways, right? So depending cross product with the right hand rule, so either this way, right? So as you're going to go, right hand rule. So it's either going to be this way, okay, or it's going to be the other way. So that's the only change that you have. But it wouldn't change your volume if you're taking the absolute value of your final result. Now, if you are just measuring if it's coplanar, all you're looking for is if the result is 0 or not. As long as you get a non-zero, it just means it's non-coplanar. All right, so that is it for this video. Thanks for watching. We'll see you in a future video. Bye, everybody.